Welcome to Circuitvalley. I'm Gaurav. This video is going to be a continuation of my previous video where I showed you how you can interface a MIPI camera to a Linux SoC. In this case, we are using Xilinx ZCU106. Previously, we used Xilinx ZCU102. So last time I showed you how you can interface this camera to a Linux SoC, stream video from camera into SoC's RAM. And in this video, I'm going to talk about the next solution. The next solution is to put some storage. So I'm going to show you one more project of mine. This is the NVMe FMC carrier. So this particular board allows you to connect two really fast NVMe storage to a Xilinx FPGA board or any other board that has FMC connector with the PCI lanes on it. When you are working with such a high performance peripheral such as camera, they stream quite a bit of data, and when you're trying to store that data into a FPGA, you will soon turn into the limits of the storage. And as they stream quite a bit of data and quite fast as well, also with very low latency, so you will not be able to store this much data into a SD card or even in a RAM disk for that matter. You would need a large amount of storage. So for that particular reason, I decided to design FMC carrier board so that I can connect two NVMe storages to the Xilinx ZCU106 board. Why did I switch from Xilinx 102 from last video to Xilinx 106 in this video is that this particular FPGA is an EV series of SoC from Xilinx. This has a built-in video encoder, so you can encode the raw video coming from the camera into H.264 and record it into NVMe. In this particular video, I'm going to only focus on this NVMe hat, how I designed and constructed this NVMe hat so that you can have your own storage and have as much as of space, and that is also very fast space. This allows multi-thousand megabyte per second of transfer, and you can easily record even raw video if you wish to. We will at some point try to record the compressed video from the video encoder, which is built into Xilinx 106 FPGA. So this board, of course, you can plug into any FPGA board which has PCI lanes on it, and if you have a Linux running on it, then you can very easily get it up and running. So in a minute, I'll show you how easily you can design your own solution in 10 minutes, and you will get this NVMe storage connected to your FPGA. I'll show you first the Vivado design. Very easily integrate Xilinx XTMA IP into your FPGA design, and with that and the help of the Linux system, you can easily get your NVMe storage up and running and ready to be used in the rest of the design. This of course allows you to connect two NVMe storage, has status LED and power status LED for both of the storages, allow you to connect different size of the NVMe's, and on the back side you can see it also has the socket of the NVMe, socket of the FMC as well, so that you can stack multiple boards. And this is how you got the complete solution. Camera data comes in, goes into the FPGA, get converted, store it into RAM, and from RAM you can put it into the NVMe storage. You can of course stack one of my this GPIO hat or this breakout board on top of this particular board, and you will have a totally proper solution if you want to do some kind of filtering or some kind of specific controls over the camera and lights or any other real-time control or frame sync between different cameras. Then you can achieve that with this particular solution. This is the PCB of the board, a 8-layer board, very high quality board, built with impedance control and taken everything into this consideration. Very well done, very well designed, and supports 4 different size of SSD, total big size of 2280 SSD and up to smallest 2230 SSD. Of course, it has threaded offsets, so it allows you to easily screw in the SSD and you can plug it in and stack it. Of course, you cannot stack two NVMe hat on top of each other because they occupy the same pins, and those same pins are of course not routed on top because of the signal integrity. So, but you can of course stack this solution, or you can also stack this particular board on top of the NVMe hat, and because this uses only LPC connections, while our hat uses primarily HPC connections. So now I will move back to Vivado and I'll show you how does it look on the Vivado. So now we are at Vivado, and now I will open the block design and show you that how easy it is to interface NVMe storage. So to interface NVMe storage, you will need XTMA IP. So this particular IP, what does it allow you? It gives you this NVMe or PCI lanes, 4 of the PCI lanes, something like this, and this allow you to connect it to the NVMe storage, and this particular IP allow to bridge between this XC bus and NVMe. So this IP get controlled by these two interfaces. This is the register interface, and there is another interface. So this get controlled by the master XC port, and primary data transfer happens on this particular port, which connects through this slave high performance port on the Zinc UltraScale Plus. So these are the primary components: UltraScale Plus FPGA, XDMA, and so that you can connect XDMA to UltraScale Plus, you have a smart interconnect for the XC, and you have another smart interconnect for the primary data path. You of course need to specify the clock, and clock need to be spatial. It's clock coming from GT, so you have to use, what do you call it, this GTE buffer. Generally you can just select the PCI ref clock here, and it will automatically select appropriate buffers for you. You have to connect this something like this. That's GT clock goes to GT, and divided by 2 clock goes to sys clock. And one more thing you need to notice is that this XC interface clock is generated by this IP. Generally, Zinc UltraScale Plus generates XC interface clock from this particular signal, PL clock, but in this case, Xilinx IP will generate. What else you need to take care? You need to take care of the peripheral reset. It is absolute mandatory and absolutely needed. Without that, your IP or your NVMe will never get detected. It's mandatory for all the PCI devices. They need to synchronize the reset appropriately. In my particular board, reset is connected normally, and this particular device expect different reset, so I have inverted it, and my particular board expect, NVMe devices expect active low reset. So if you pull it low, then device will go into reset, and this is particular device is somehow active high reset, so I have put up an inverter there, and this is just a synchronization. So same module happens for another NVMe as well. This is for XDMA 0 for one NVMe, and this is XDMA 1 for another NVMe. Same buffer, reference clock. I have 2 reference clocks incoming, 2 NVMe storage, and 2 NVMe PCI Express 4 peripheral reset, and that's it. That's all actually you need to connect to an NVMe device from the FPGA side on a Zinc UltraScale Plus SoC. If you're not having SoC and you only have FPGA, I would pretty much recommend that you maybe try to focus on having a soft-core CPU, because these things are a little bit not that easy to maintain or manage in the FPGA itself. SoC in this particular situation helps really greatly. And you need to configure this into XC bridge mode and select advanced mode so that you can select the root port. You need to specify the location where it's going to be. This depends of course where is your NVMe connected, which particular block of the GT block. So I have both of the NVMEs connected, so I have of course used up both of the blocks. And here you can choose the data width. NVMe generally required cross 4, so you have cross 4 here, and address width you can leave it default or you set it to 64. Here you can choose the NVMe, you can choose the XC data bus width, which generally doesn't matter. It depends on how much resources you have available and stuff like that. The PCI ID you have to choose here that you are doing a bridge device, and PCI to PCI bridge. And this PF bar, we don't need PF bar, and we need to enable that MSI interrupts are needed for NVMe storage, so you need to enable this. And XC bar, you need to specify the address. This particular address you need to specify for the registers, so that and for the Xilinx, so that the Linux environment can access. This is the same address as the XC bus address. I'll show you in a second from where this particular address comes up. And other than that, you don't necessarily need to do much. You just have to enable primarily that it is a root port with which area, which kind of device, and of course you need to enable these MSI interrupts, because they are absolutely mandatory. Without that you cannot use NVMe storage, and specify the correct address here. This will be specified in the ranges and everywhere else. Now I will tell you what those addresses in the bar area. So if you go into this area, this particular address need to be entered. If it may be different for you, generally it's the same address because it's quite important of a component, and Vivado automatically have reserved spaces for it. And these are the addresses you need to specify, or it will automatically assign. If you remove them, it will automatically assign this A and B address for first and second IP, and these particular addresses will automatically assign. These all addresses will be written into the device tree ranges. I'll show you how you can get this thing recognized under Linux, and how this NVMe storage will get recognized under Linux, and you can easily access them, mount them, and we will do benchmarking as well. I'll show you how fast they run by themselves, and how easy it is to get the NVMe working under Linux. So Vivado thing is done. We will build it and let it run and synthesize it, and once we have a bit stream, we will move to Linux. So this is how the device tree overlay looks. This is a basic overlay. First fragment is the FPGA bit stream. This is very generic. And second fragment, you can see I have specified two PCI buses, DMA0 and DMA1. Both are device type PCI, and both uses Xilinx XDMA host driver because they are root ports on the PCI. And what is more important is the ranges. This particular fragment I got from the Xilinx default XDMA template. So these are the ranges it specify. Of course, these are not correct for our application, and this is the correct range for our application. This is the address of our register base for A and 7 times 0 for the first IP, and B 7 times 0 for the second IP. So these ranges, both of these ranges, they are very, very important. What next is important is interrupt. Maybe I'll go back and show you one more time. It is very, very important, as I told you, that interrupt, MSI interrupt, both of the MSI interrupts are needed, and in the end they will be concatenated and go to the Zinc UltraScale Plus. This is first offset is, I believe, decimal 89. So 89, 90 and 91, these are the 3 points or 3 interrupt. First is a normal IP interrupt, and 2 of them are MSI interrupt, and next is the normal interrupt for the XDMA1, and these are the 2 what do you call them, MSI interrupts. And these things are very much important, and you need to specify the interrupt controller, and they value directly reference to this particular interrupt controller, and this is how they map. And of course interrupts are specified MSI 1, MSI 0 and MSI 1. That's all you need. Let's turn it on. Board has turned on. Of course it is showing you that init B is not done, that little red LED in the corner. So now we will see on the terminal that it boots into Linux. It's the default Beta Linux or Xilinx default Linux, nothing special. I have customized the kernel. I'll show you in a second what are the customization I have made in the kernel to get the NVMe drive working under the Linux. A default kernel from Xilinx, of course, does not ship with all the drivers and necessary modules enabled. So you need to keep a little bit eye on it, which modules are enabled, which are not. But the default bootloader and everything else is default. You don't need to do anything. Root file system is also default. Only the Linux kernel has been again recompiled so that we can have NVMe storage or the NVMe drivers. So we have this board booted in AMD EDF, and if you do LSPCI, of course it will not show you anything because the device tree is not loaded. I have configured the device tree to be a device tree overlay, and for the sake of showing you the D message, if you are following along or you're trying to debug your own system so that you know how my system looks, this is my D message. It's a little bit fast maybe. I'll show you slowly that there is no PCI mentioned there anywhere at all, and it boots normally into somewhat default of a system. And now we will load the binary using FPGA utils. So the device tree is of course loaded, and now both of the root ports must be recognized. Root ports are recognized, just to show you what is the D message, how it gets loaded, and so that you can follow along if you're trying to debug. This is how it looks once I have loaded my device tree. So last few message 116 seconds onwards are from the device tree load and overlay load. So it shows you that it does not see any link up because it gets loaded in such a situation that it does not even maybe try to link up. We can do a rescan, and they will see that device get detected. So now we got our device detected. Both of the NVMe storage, the Samsung, this 256 GB, the second-hand device which I had, and another SN770M. So this particular solution, it works reliably well for almost all the SSDs. I would say that there may be some oddballs out there, but it'll work for most of the SSDs. And maybe we'll do ls block so that we can know that our NVMe got detected. So both of the NVMe's, one is 238 GB, another is like 1 terabyte, almost 256 GB and 1 terabyte, both of the SSD detected. We will soon mount them and do benchmarking on them. But before that, I'll show you that you need to enable certain things on the kernel side. So now we are into the kernel menu config to show you which device drivers I have specifically enabled. So I'll go into the device drivers, and of course you need the PCI support and PCI bus support. This particular option is not by default enabled. You need to enable it. And NVMe support is also by default not enabled. So you have to enable these NVMe Express block support. You can enable like all the different options if you choose to, because I was experimenting, so I have decided to enable everything. Not everything is needed. And what else you need to enable is somewhere there must be a PCI controller driver. Yeah, this is the PCI controller driver. Xilinx DMA PLI host bridge support. So these particular drivers need to be enabled. First is PCI Express port, second is this PL driver, and third is the NVMe Express block device. So these are the three drivers you definitely need to enable. Without that, it will not work. By default, the bus driver is not enabled and NVMe driver is not enabled. Everything else is generally enabled, but that's also a catch, that you will see your PCI root bus, but you will not see your NVMe device. So let's move back there and we will do a benchmark test, and we will see how well it works. So to do benchmark, first we will mount them. Maybe I'll mount them at the media and make two folders, NVMe 1 and 1P2. Yeah, this is NTFS. Maybe I'll mount the other one first. MKDR NVMe 0 and 1P1. So now the device is mounted. You can see there is few tests which I did previously, and let's see if we can do the test one more time. So we will use time command and we will use dd, and we'll try to run the test on the first partition or the first drive. I have mentioned the wrong name actually. So I'll issue these commands with time, and we'll see how much time does it take. So while it's running, you will see that so it took around 3.7 seconds and took around 1.4 gigabyte per second or something like that. So this is pretty fast, and the results which are available online are also similar. You can get around 1000 megabyte per second or 1200, 300 megabyte per second. Not really more than that, because it is being limited by the CPU itself, not by the FPGA. And you can have two NVMe's and both of them working at around 1000 Mbps each, which can give you around 2200 or 2100 or around 2000 Mbps megabyte per second each, which is 2 gigabyte per second, which is quite a bit of plenty data. You can do a lot of in this much bandwidth. So maybe I'll let it run the test a little bit longer so that you can see the status LED blinks a lot. The status LED of the SSD, how does it show you? So there are two LEDs on the corner. One LED is here. These are bicolor LEDs, and these are the power and status LED or power and activity LED. So while you're writing to the SSD, it's showing you the activity. So you see that writing a lot more data has slowed down a bit, and that has to do with maybe the cache, and this SSD is also not the best. We will try the other SSD with the large read and write as well, and we will see how it goes there as well. So we'll read the same amount. Yeah, now I understand why it's invalid argument. Need to be I flag. So now we're ready. So this is the read, and we read quite fast, around 2500 gigabyte per second. It maybe has to do something with the cache as well. Maybe we'll try to read other file, which is test3 or something like that, and see if it is any slower or any faster. So it's a little bit, I guess, smaller, same size of file, and it reads the same value. So this is the read performance, and this is the write performance for you. Reading goes really fast, 2.5 gigabyte per second for this particular Samsung small SSD, and writing goes also similar range, around 1000 megabyte per second. But we are not here to benchmark the the NVMe SSDs. We are here to benchmark our interface, which achieves 2.5 gigabyte per second read and 1.4 gigabyte per second write performance. So just to show you one more time that what is the LSPCI looks of both of the SSDs. These are our SSDs, and this is the root port actually. This is the root port, and this is our SSD, first one. And you can see this SSD is Gen3 SSD, of course. So you see this link support capability 2.5 to 8 GT, and this is the smaller, older 256 gigabyte Samsung SSD, and our current link speed is 8 giga transfer per second with the 4x bit. So our NVMe SSD is appropriately connected and working fully under 4x lane and with the capability of 8 GT. And this is another SSD. So both of our SSD works fully up to the capability in the 4x bit and up to their performance. So they work really, really well. So I guess that's it for this video. There's not much more to show. And if you want to see the PCB schematic and everything else, if you want to see the PCB and pinout diagrams, then you can visit my website www.circuitvalley.com.